Okay, so good morning. Welcome to the uh, basically last full class week. Um, the plan for today is to just continue on with correlation and regression. We discussed correlation a little bit last time and regression maybe a tiny bit. We're just going to quickly recap those concepts, talk a little bit about regression, a couple of details, couple kind of background details related to some of those topics, and then we're going to look at applications on Excel. And then next time we're going to finish correlation and regression in the Excel demos and probably start chi-squared goodness of fit test. And then on Monday, the 6th, note that we do have class, regular scheduled class Monday, the 6th. Final exam week goes Tuesday through the following Monday. So next Monday, a week from today, we'll wrap up a couple of these topics: chi-squared goodness of fit, chi-squared independence test, and chi-squared test for independence, and ANOVA, analysis of variance. Like I kind of mentioned before, for both correlation and regression and ANOVA, these are fairly deep topics that that could take up an awful lot more time than we're giving to them. So we're just kind of scratching the surface of these last couple of topics in the course. And as I also mentioned, I will post supplemental videos on chi-square goodness of fit, chi-square test for independence, and ANOVA. That way, if you want to take the final exam a little bit early, so if you want to take it the weekend of the 3rd, 4th, or 5th, that way you can take the final exam and you'll have access to the information for that final exam and not have to wait until Monday's class to get that. But we still will go through this on Monday, so whatever works for you is fine. On the 8th, we'll have an optional review session, 10:30 to 12:30, same Zoom link as normal class. And basically, I plan to just kind of treat this like office hours, but if we do have several people show up, we'll treat it a little more like an exam review session, kind of pick a topic that's, popular that people are asking about, and then maybe do a couple problems in that topic and so on. But if it's just, one person here or there that pops in, we'll treat it more like office hours, and we can go over individual problems or individual questions that you have. So it'll be a fairly informal review session on the 8th, just because we have to do something during regularly scheduled exam time. But the final exam is scheduled for the week of the 3rd through the 10th, and it's taken on my stat lab with Examity, same setup as the midterm exam. And make sure that you plan to complete the exam at least a couple of days ahead of time. I would recommend Wednesday at the latest. That way, if anything goes wrong, if there's any kind of tech glitch or something like that, there's plenty of time to work it out. So just being the end of the semester, we're really up against time constraints, no due date extensions on the exam. So definitely do not want to, wait until the last day or the last minute to take the exam and then have something happen and be in that situation. And when I copied this over, I copied that as well. So there we go. I think that is all the administrative stuff. I know I've said this a couple of times already, and say it in the next couple of classes as well, just to make sure that we're on the same page. I know you all have a lot of exams and presentations and papers and things all going on, so I try to remind you about where we're at in these last couple of weeks. Okay, so before we jump into correlation regression again, are there any questions from last time? Okay, so I want to just quickly review what we talked about last time with correlation, because this is going to be really important for us to understand in order to understand regression. So remember and I'm going to go through this much quicker than last time. So if you missed last time, make sure you go back and watch that. I discussed this much more thoroughly then, but I'm going to go through just a crash course reminder right now. So remember, the goal of correlation regression is to study the linear relationship between two variables, x and y. So we think we have like data point I, 1, 2, 3 through n, and we have paired data, x and y. And the kind of typical example, the canonical example, is a person's height and weight. So maybe this is height and this is weight. And I choose one person from the population. For that person, I get their height and their weight. So that's paired data. Both of those data points belong to that one person. And I can make a graph for person number one of their height versus their weight. And same for person number 2 and 3 and 4 out to person N. And we have something like this. We would say, okay, we have a scatter plot representing this data set of paired heights and weights. So each dot represents a specific person, and the location of that dot represents their height and their weight. And then we said that, well, both the idea of correlation and we'll see of regression is this idea of a linear model. There are some data sets, like say the height and weight data like this, that seem to be reasonably able to be represented by a linear model. And there are some data sets, maybe like this one over here, that's just kind of scattered about. We can see that I could find, now there are some lines that do a terrible job of modeling this data, of course, but I can find a line that does a decent job where most of the data points are pretty close to the line. But for this example over here, any line I choose, there's like no good choice for a line that does a decent job of modeling this data that's just kind of scattered about. We said sometimes one trick for being able to see this a little better is you pick roughly the middle of the data set and you draw a set of axes there. And I noticed that I've got a lot more data in quadrants 1 and 3 than in 2 and 4. That might suggest kind of a positive relationship that when X is high, Y tends to be high, and when X is low, Y tends to be low. But I don't see such a relationship for this data over here. It seems like there's about as much data in any one quadrant as any other quadrant. So if I, knew that X was high, if I knew that I'm kind of on the right side or that I'm in quadrants 1 or 4, I wouldn't have a good estimate of whether I think that I'm in quadrant 1 or quadrant 4 based on knowing that we're to the right side. Where for the height and weight, I would. If I told you, well, it's the data point I'm looking at is in either quadrant 1 or 4, you would, take if you had to bet which one it was in, you would bet on quadrant 1, not quadrant 4, and vice versa for the left side. If I told you it was in quadrants 2 or 3, the data point I'm looking at, you would bet quadrant 3, there's more data down there. Okay, so then we talked about the, I don't know why all this came over here so strangely, but let me see if I can. I didn't intend for this writing to actually come over as well, but maybe we can actually make use of it. Let's see. All right, so there we go. That lined up nicely. Usually the writing doesn't copy over correctly in OneNote, but there we go. So my correlation coefficient, the next thing I wanted to discuss, we actually have my notes from last time that came over for some reason. Every once in a while, OneNote, when I copy text, it just copies kind of crazy. Like it'll do something like this, like copy all of the writing below it or something, or all of my equations will get messed up. And then usually I just go in and like delete it and copy it again and it works fine. So I don't know. I just didn't notice this time that it had copied all of this below, but it seems to have worked out okay. So if you think that AI is going to take over the world, then maybe just look as far as Microsoft Office and maybe it won't do it so quickly anyway. But again, the correlation coefficient we discussed last time, it's a number between -1 and +1 inclusive It has the notation either R for sample correlation or rho, the Greek letter for population correlation. And we're interested in two things. Number one, the magnitude. In other words, in absolute value, is the correlation near zero or near one? If it's near zero, there's lack of evidence of a linear relationship between the two variables. And if it's near one, there's strong evidence of a linear relationship between the two variables. If the magnitude is near zero, we don't really care what the sign is, because if there's no relationship, we don't care about the nature of the relationship. The relationship isn't there. But if the magnitude is near one, in other words, if the correlation is near either -1 or +1, then we do care about the sign. We're saying there exists a relationship, and now we're interested in knowing the nature of that relationship. Is it positive or negative? In other words, is it true that higher values of one variable are associated with higher values of the other variable, and lower values of one variable are associated with lower values of the other? If that's true, then we call it a positive correlation. If the opposite is true, if higher values of one variable tend to be associated with lower values of the other variable, and lower values of one tend to be associated with higher values of the other, we call that a negatively related or a negative correlation. So we basically have three kind of rough qualitative descriptions for correlations: near negative one, where we have a strong negative relationship; near zero, where we have lack of a linear relationship; and near positive one, where we have a strong positive relationship. Note that a correlation near zero doesn't necessarily mean there is no relationship between the variables. We're only searching for linear relationship here. So we could have a relationship like this. Maybe this is something like speed versus miles per gallon. So like miles per hour that we're driving versus miles per gallon fuel efficiency. There's certainly a relationship here. I mean, if I, know where my speed is right now, I am pretty certain what my miles per gallon are. And if I know what my miles per gallon is, I know a little bit about my speed. If I know that my miles per gallon is low, I know I'm probably either going pretty slow or pretty fast. I'm probably not going a moderate speed, right? The faster that we go, the more air resistance impacts us. So that's why it drops off again on the right-hand side. And of course, if we're just sitting at a red light or something, we're burning gas and not really going anywhere. So something like this, well, clearly there's a relationship here, but there's no kind of good linear model. There's no straight line that does a good job of modeling this data. So the relationship is kind of fundamentally nonlinear in nature. So this would also be a correlation near zero. So a correlation near zero doesn't really mean no relationship at all. It means no linear relationship between the two variables. Okay, let's move down to regression then. So what's the idea of a regression line? Well, let's again think back to our height and weight example. And I have my data like this, and maybe I run a correlation on Excel, and it tells me your correlation between height and weight is 0.8. Okay, that's nice. I see that I have strong evidence of a positive linear relationship. And what I kind of mean by that is that I think that there is a line, a straight line, that would make a good model for this data, that where I could draw that line and most of the data points would be pretty close to that line. What's the idea of regression? The idea of regression is to find this line. So this line would be given by y equals alpha plus beta x. Here, alpha is the intercept and beta the slope. Typically, we're more interested in beta than alpha because we're typically interested in the relationship between the two variables, which is really captured by beta. So if X changes a little bit, that change has to pass through beta to be reflected in Y. So that's more, it's a stronger indicator of the relationship between X and Y. But alpha is, of course, an important part of the model as well. We have a line has both an intercept and the slope. And we would approximate this line with y hat equals a plus bx. This is also an intercept and a slope. We would think of alpha and beta as being population parameters. So if I had access to the whole population and wanted to construct a linear model, alpha and beta would be the numbers that I would use. But if I have access to just my sample, I use A and B. And like I kind of mentioned before, I'm not going to really make a big deal about the difference between the two. Because we're just scratching the surface of correlation and regression, I'm going to use the two basically interchangeably, kind of like I did up here with correlation. But at some point, we will be talking about things like hypothesis tests, based on the hypothesis test related to the slope variable B or beta. So, I mean, it is important to understand that qualitatively in the background, there is an idea of population parameters for alpha and beta for the intercept and the slope, and of sample statistics based on the data that we actually have. So that same idea from chapter 7 on is still here, but we're just not going to make such a big deal about it. So now, if I look at this red line, this looks like a pretty nice model. But if I look at, say, I guess somewhat ironically, if I look at the green line is not a good model. So the red line, just looking at it, we would say, yeah, I think that's a pretty good model. If we look at the green line, we look at that and say, well, I think that's not such a good model. Why would we say that the red is good and the green is not good? Well, I think the main thing that we would look at is that the red line tends to be close to most of the data points, and the green line, I mean, it's close to a few of the data points, but there are a lot of data points that are quite far away from the green line. So how can we come up with the idea of a good linear model in order to find the best linear model? Well, let's say I'm just going to draw a few data points. We probably wouldn't want to actually make a model based on only 4 data points, but just to illustrate, I'll just draw 4 of them. And if I draw a line, let's just make it a pretty good line to begin with, a pretty good linear model. If I want to know how good is this linear model versus, say, one that looks like that, for instance, what I might look at is the deviation of the individual data points from this line. I might look at these 4 distances. In other words, kind of what's the goal of this linear model? The goal of this linear model is to say, okay, I have a point here. Let's call this x1, y1. Maybe this is for data point 1 for person number 1. I have a model. So if I was at position on the x-axis, x equals x1, the point that I see on my regression line here, we'll call it y1 hat. x1, y1 hat. y1 hat is an estimator of y1 basically, right? y1 hat would be the guess that we would make from our model at the output given the input x1. But our data says the actual output that we observed when x was equal to x1 was y1. So y1 hat is an estimator of y1, but we see that it's not exactly the same number. So our error one, looks more or less like y1 minus y1 hat, that difference. But again, if I just computed all of my errors and did something like adding up my errors, well, then I would have a lot of cancellation. I'd have some positive errors, some negative errors. I could actually make really big errors as long as I made the big errors in both directions. If I made some big positive errors and some big negative errors, they cancel out. But I don't think that would be a really good model, right? Having a model that is like either terrible in this direction or terrible in that direction in a coin flip, that's probably not a good model, even though kind of on average it hits the middle. So really, I'm interested in something like maybe an absolute error, but we saw that absolute values are a little annoying to work with, or maybe a squared error, making each of these errors positive, regardless of whether the data point is above the line or below the line, lets me add them together, and then they don't cancel each other out. We saw this same idea several times before, but first in the variance, when we constructed the variance and how it works. So really what I want to do is I want to take my data and so I have my data set. This is fixed. This is known. This is what I've gotten from the real world. And then I want to find my y hat. So y1 hat for a given line, for a given linear model with a certain intercept and a certain slope, what would be my estimate for y1 when I plug in x1? I have an actual y1 from the data. I have an estimated y1 hat under my model. And I do that through yn. I do that for each of these lines. And this is based on y hat equals a plus bx for some choice of a and b. Now, for some choices of a and b, my errors like y1 minus y1 hat and so on, and yn minus yn hat, or really my squared errors, right? For some choices of a and b, these squared errors are going to tend to be pretty small, like maybe this one up here for this line. For other choices of a and b, I'm going to get a line like this where I'm going to have quite large errors. I can go to the bottom of this column of the errors, the individual errors, and add them up. We call this the sum of the squared errors. Sum of the squared errors. And it's just as it says. We take the errors, we square them, we add them up. If this number is fairly high, if it's a large number, we have a lot of substantial errors. If it's a small number, then our line tends to be, in some sense, on average, closer to our data points. We would prefer smaller sum of squared errors than larger ones. So if I'm comparing two lines, one choice of A and B versus a different choice of A and B, and I want to know which one is the better model, I might look at the sum of squared errors for the two models and pick the model that gives the lower sum of the squared errors, because that means that in some sense the line tends to be closer to most of the data points on average. Or if I want to look across all choices of A and B, A can be any real number, B can be any real number. My math problem now becomes to choose A and B, to be the numbers such that we minimize the sum of the squared errors. This is sometimes called the least squares, or something like the least squares method. Least squared error, or something like that. So this is the idea behind the regression line. We have a lot of different models we could choose. We could choose a bunch of different values for A or for B. That gives us a bunch of different potential linear models, infinitely many. How do we pick which one is the best linear model? The best linear model is the choice of the intercept and the slope that minimizes this sum of the squared errors, where we take the estimate under the model for a given input, x, say x1, x2, whatever. We compare that to the actual data, the actual y value for that x. We take their difference, that's the error. We square it to make sure that it's always positive. And then we add them all together. That's the sum of the squared errors. And we choose our intercept and slope. We choose the line that minimizes that sum of squared errors. It gives us the least squared error. So now, practically speaking, how do we do that? I have to search through infinitely many lines. That's not really feasible. Even if I had to choose a whole bunch of A's and B's, doing this by hand is going to be a huge pain. There are some formulas to do this. The formulas written out in something like summation notation are pretty cumbersome and annoying to do. They're not realistic to do by hand for any reasonable size data set. So practically speaking, we lean on the computer to do this. So this is a computer problem. There are closed form expressions for this. You can use a little bit of calculus, and actually, if you've completed Calc 1 and you've taken a logical leap or two, you can probably figure out how to solve this problem. If you've completed Calc 3, it should be pretty trivial to solve this problem. So it's not like no solution exists. There are solutions, but the formulas for A and B are kind of annoying. If anybody has seen linear algebra, I think we have some folks who are going into like computer science or more techie fields. B is actually very nice. In linear algebra notation, it just turns out to be this. So it's actually, there are a lot of things that are very messy when you try to write it out in kind of standard algebra notation. But if you make the switch to linear algebra notation, everything works out beautifully and you get very elegant solutions. There's a couple of things like that. This problem is one of them. This is just a super pretty result. If you looked at all the summations and all that for A and B, you're like, geez, that's going to be a mess. But in linear algebra notation, it works out very nice. Another example of that is modern portfolio theory, Markowitz theory, where it's basically the idea that like you don't want to put all your eggs in one basket. You want to diversify your investments. The results of that are also very nice when written in linear algebra. So if any of you are currently taking linear algebra, or if you see that, if you're taking it in an upcoming semester, there's a little plug for linear algebra. But anyway, we are not going to worry about the closed form solutions. We're going to ask Excel to just use its built-in functions to find A and B for us. And then we're going to focus on understanding what A and B mean. Now, a couple of notes that I want to make here. So what does this do? This finds the best linear model, at least under some idea of what the word best means, under some idea of what a good model is. But the thing is that the best linear model isn't necessarily a good linear model, right? Kind of like, if you took a whole bunch of, folks who look like me and we all decided to run a marathon, one of us would have the best marathon time, but we wouldn't be, on Eliud Kipchoge's heels, so we wouldn't be good marathon runners, even though one of us would be the best of the candidates that you put forward. So we could have a situation like our just scattering of random points like this, where we had said before, I mean, there doesn't seem to be really any good linear model for this, right? Where we said before that the correlation was near zero, there's no good linear model, right? The goal of regression is to extract the information about the nature of the linear relationship. But if no such relationship really exists, well, I mean, if we go through this automated process, it's going to give us something. I mean, there are extreme cases where it'll just blow up, where you're like dividing by zero, but that would be quite the extreme case. It's almost always going to give you something. It's going to throw out some model for this data. Maybe it looks like that. That's the best that it can do, but it might be a terrible model. There are going to be other situations where we have, say, like our height and weight data, a data set that looks like a linear model could pretty reasonably do a good job of modeling this. So here, row, I don't know, maybe say 0.8 for the correlation. It's a number that's near 1 in magnitude. It's near +1 or near -1. So there does seem to exist a linear relationship between the two variables. And now when we extract information about its nature, we get something meaningful. So this is probably a good linear model. Sometimes the best linear model for a given data set is a garbage model. Sometimes the best linear model for a data set is quite a good linear model. That's an important idea. When we solve this problem, choosing A and B to find the best linear model, the resulting model might be garbage, or it might be good. So just because we found the best one doesn't mean that it's a good model and we should take it and run with it. And that's what our investigations using these Excel spreadsheets are going to look at. There is one more detail. Let me check my notes over here. Yeah, one more detail that I want to discuss. And then one little kind of side note. So I mentioned that finding A and B are quite annoying. But let's consider that we have a data set. Again, we're not going to do this by hand, but I want to show you this just to give you an idea of particularly where B comes from, where the slope comes from. What do I have? X1 and Y1 through Xn, Yn. Now I can look at each of these lists of numbers, X1 through Xn or Y1 through Yn. I could look at them individually, and I could get, I'm just going to use population parameters here because I don't want a bunch of bars floating around like X bars. It's going to maybe get a little messy, but I'm just going to call this mu X and mu Y. I could look at my X1 through Xn and I can compute a mu X, right? Just a mean for that data set. We'll just call it population data. And the same for Y. We could do this back in chapter 3. I could also compute a standard deviation for X and a standard deviation for Y. If I look at those two lists kind of individually, right? X1 through Xn, I can compute mu X and sigma X. That's a chapter 3 problem. If I just look at X1 through Xn, I could do the same for Y1 through Yn. So what can I do now? I can transform my random variables, or my data, sorry, transform my random variables, but I'm going to apply that transformation to my data as well. I'm going to call these X tilde and Y tilde. So what is the relationship here going to be? Well, for x tilde, I'm going to take x. I'm going to subtract off its mean and divide by a standard deviation. I'm just going to get a z-score for each of my xi's, a z-score relative to the x data. So I'm going to get like x1 tilde. I guess I could really just call it like z1, but I'm going to do the same thing for the y's. So I don't want to call them both z. I'm going to get x2 tilde and so on through xn tilde by just taking each of my x1 through xn, subtracting off the mean of the x's, dividing by standard deviation of the x's. I'm going to do the same thing for the y's. I'm going to get a z-score relative to the y data for each of the yi's. So y1 is going to become its z-score, which I'm just calling y1 tilde. y2 transforms into y2 tilde, so on through yn tilde. So now I have a different data set, obviously related to the first one, but I have a different set of n ordered pairs, x1 tilde, y1 tilde through xn tilde, yn tilde, where these are all kind of z-scores for their respective data sets. Well, it turns out actually that if I do this, this makes the modeling a lot nicer. And what I end up with is that my beta hat or my B is just going to be the correlation between the x tildes and the y tildes. So my slope is just going to be correlation between these two. And it turns out that the intercept will be 0. So this is called demeaning. It's not like demeaning like when you call somebody a bad name or something, but demeaning like taking away the mean. When we demean our two lists, that takes that kind of crosshairs idea from, where was it, up here? From up here. It just basically takes this crosshairs and pulls it back to 0, 0. So that's what makes our intercept 0, taking away these means. And then dividing by the standard deviations means that our slope is just the correlation. So if I have a model y tilde equals alpha plus beta x tilde, the relationship between these two variables, x tilde and y tilde, is the standardized versions of x and y. I end up with just y tilde equals rho, maybe I'll call it rho tilde, the correlation between the tilde, the standardized forms, x tilde. So I see that that in this situation, after I've gotten z-scores for everything, the correlation coefficient between the tildes is what gives me the slope of this line, and the line always goes through 0, 0. So that's kind of nice, right? We can see that there's a very direct relationship between the correlation coefficient and linear regression, but we only really see it explicitly after we've gotten z-scores for everything. That kind of makes sense too, right? The correlation coefficient is unitless. And if I didn't z-score everything, my x's and y's up here would have units. So, I mean, if I change the units, I change the nature of the problem. So, I mean, beta couldn't be like a unitless quantity, really, right? I mean, it shouldn't be something like a correlation coefficient, where if I change the units, I'm changing the nature of the problem. So, I don't know. I think in some kind of like gut feeling way, this kind of makes sense that things work a lot nicer when we've standardized than when we still have units floating around. But here we subtract off the mean, divide by the standard deviation. And that makes this relationship between the correlation coefficient and linear regression really kind of come to the forefront. Okay, so two more ideas. These two will be a little less, I guess, a little less technical. So you might be looking at this and saying, okay, I mean, that's nice that I'm getting linear models, but I have lots of nonlinear phenomena, right? Like things that aren't related to one another linearly. I don't know who said this, but it's kind of a funny little quote that dividing the world into linear versus nonlinear phenomena is like dividing all objects in the world into bananas and not bananas. In other words, like, why the heck are we making so much of a big deal of studying linear models or linear equations or whatever linear phenomena we're looking at in some math course when, essentially the likelihood that we come upon a situation that is truly linear in nature is very, very unlikely. It might seem silly. It might seem like a silly exercise that we're trying to develop linear models for things that are almost certainly nonlinear. But one of my favorite, or probably my favorite professor, one of my favorite grad school professors, Professor Bill Layton, he's retired now from Pitt, but he would always say the world is locally linear. So what does this mean? Well, this means that if you, don't believe the earth is flat, if the earth is a sphere, and if we're looking at the earth from standing on the moon or something like that, say, okay, the earth looks like a sphere. It would be kind of dumb for me to look at the earth looking like a sphere on the moon and try to model it with a linear model or a line or something like that. I'm not going to be able to do a good job. But what if, I don't know, where are we? Maybe something like here. What if I'm standing on the surface? Let's just pretend the earth is a nice, perfect sphere. From where I'm standing, I mean, the earth is like almost completely flat, right? Or if I'm on, say, the water or something like that. From where I'm standing, if the earth was a perfect sphere, or if I'm on water, nice still water or something like that, it's almost perfectly flat. So over here, I mean, yeah, there might be a little bit of error if I model this with a straight line, but locally, when I zoom in far enough, a linear model does an excellent job. Globally, this looks like a silly model for the surface of the earth, but locally might be a great model. And quite often we're interested in how things relate to one another locally. I'm not interested in, in theory, how much somebody will weigh if they're like, 7 foot 8 inches tall or something. I don't know, it's probably like, the tallest person in the world or something like that. I'm not interested in that person. I mean, they're so far outside the norm that that I can tolerate my model not doing a good job at that extreme. Or for somebody that's, an adult that's like 3 feet tall. It's like, okay, they're far enough outside the norm that if my model doesn't do a good job over there, I'm okay with that. But does my model do a good job for like between 5 feet and 6 feet? If I want to estimate weights based on heights, and I could estimate well within that range, again, our kind of theme for the course, all models are wrong, some models are useful. That's probably a useful model. It's not a perfect model, but it's probably useful. So this idea that the world is locally linear, this is also something that if you take calculus, that's one of the big ideas in calculus is the idea of a linear approximation being a good approximation to a function locally, provided the function is nice and smooth and so on. So this idea is really what comes to save the day, that we model nonlinear problems by linear functions because, one, linear functions are much, much easier to use than nonlinear functions in most contexts. And two, usually they're good enough. Maybe not quite as good as a more complicated model, but we're sacrificing a little bit of accuracy to gain a lot of simplicity. And another just kind of side note is, even if we have a function that is very nonlinear, we can write it as an infinitely long polynomial. So like a linear or a quadratic or a cubic, but it just keeps going forever, getting more and more terms on it. And for kind of nicely behaved functions, the influence that each successive term has on the value gets smaller and smaller. In other words, my dominant terms are like these first two here. The linear component is kind of the dominant terms. And then in some sense, the influence of the later terms might get smaller and smaller. So that's a little more of a technical, um, not being super accurate, but a little more of a technical explanation of why we care about linear models. Okay, and then there's one more thing that I want to note, and that is just kind of an interesting statistical phenomenon of mean reversion. So if you consider, if you look at couples, male, female, that have a kid, and you take a bunch of couples and a bunch of kids, and you look at couples where, say, the male is tall and the female is tall, both of them are quite a bit taller than average for their sexes. And then you look at the kid and you say, do you think the kid is going to be, when the kid grows up, do you think the kid is going to be taller than their respective parent? If the kid is a girl, do you think they're likely to be taller than mom? If the kid is a boy, do you think they're likely to be taller than dad? Given that both mom and dad are quite a bit taller than average. And interestingly, the answer is no. So if tall man and tall woman have a kid, chances are that kid is going to be shorter than their respective parent. So kind of why is that? Well, anytime that we have a model like this, and we have an extreme, so say we have extreme height, we have systematic, effects, but also random effects. So the overall is a result of systematic effects plus random effects. And so Charlie Munger in his Psychology of Human Misjudgment talk, I think it's in there. He talks about it in several different places, but he calls it like the Lollapalooza effect. It's kind of a funny name for it. But basically his point is when something extreme happens, it's kind of a confluence of several things happening to point in that direction all at once. Or if you've ever seen this phenomenon called like a rogue wave, where like somebody is on a beach and it's just like normal wave, normal wave, normal wave, and then all of a sudden there's this huge wave. Not like a tsunami, like something, crashed in the ocean and made this, but just like the overall tidal forces happen to just all, go in the same direction for that one wave and makes a big rogue wave. Same kind of idea. So we have systematic effects and random effects. If we have an extreme case, say like a very tall mom or a very tall dad, that person likely has, tall systematic effects. They have systematic effects making them tall, maybe genetic factors and so on, but also some random effects, maybe something related to nutrition or their environment or something like that. Who knows? Now, systematic effects are going to get passed on to the kid. So the kid is probably going to be taller than average because they get the boost from the systematic effects. But to have really tall mom and dad, they also got kind of really tall random effects, most likely. And in the next generation, those random effects are going to be re-randomized. So kid probably isn't going to be as tall as their respective parent, but they probably will still be taller than average. Their systematic effects will boost them above the people who don't have those systematic effects, but the random effects are probably going to be more muted in the children than in the parents, if the parents are extremely tall. Or the same thing goes for extremely short, right? Extremely short parents, not saying, something like dwarfism or something, but just folks who are quite short for systematic and random reasons, their kids are probably going to inherit some of those systematic effects, but also a different set of random effects. So the kids are probably going to be taller than the parents, but probably a bit shorter than average, though. So how does this link into what we have up here? This is kind of the last little bit that we need to talk about before we jump over to Excel. Well, if I consider, let me just write my data set down again. If I consider my data, I have my model. And maybe I think that kind of hiding in the background is this population-based model, y equals alpha plus beta x. If I think that this is like the actual relationship between x and y, then for each of these actual data points, y sub I is going to be alpha plus beta xi. That's the point that is on the model above xi, but then there's that deviation, there's that error plus epsilon I. We typically call the errors epsilon, one of the Greek letter E's. I guess depending on whether you count eta as E or A, but Greek letter E. And in a sense, this is the systematic effect, and this is the random effect. Now, our regression model, when we say we're going to do this thing with correlation and see if we think that there's a relation between the two variables, and if there does seem to be a linear relation between the two variables, we're going to do this whole sum of squared errors thing and get our best linear model, and then evaluate and see whether that linear model seems to be a good model or a garbage model. When we do all of that, there are some assumptions that come along with that process. There are some things we want to be true before we even really start down that process. And maybe I shouldn't say before we start down that process, but we want to have this in our mind before we start down that process. So the assumptions, and let me bring up my paper over here. There we go. Is that my epsilons are normal with a mean of 0 and a standard deviation that is constant and independent. My epsilon looks a little goofy. Rewrite it. So this random variable epsilon, from which we get these errors, epsilon 1, epsilon 2, and so on, these data points from that random variable. One of my assumptions for linear regression is that these errors are normally distributed with a mean of 0 and a standard deviation that is constant. If I look at my errors, sometimes these errors are also called residuals because it's kind of the residual bit that's left over after the systematic effect is taken into account. These errors are residuals. If I look at a plot of them and I see that, 1, 2, 3 through n, I guess that's I, not n over there, but just my index. And if I see that, not continuing like that, but if I see that there's like a cluster of a whole bunch that are all positive, and then a cluster of a whole bunch that are all negative, those are probably not independent. if I see that kind of at the beginning, there's a pretty small variance, and near the end, it seems like there's a much larger variance, it seems like my standard deviation is not constant. There's a smaller standard deviation for some errors and a larger for other errors. Right, so I can look at a residual plot to give me some information and to see whether I think it could be reasonably true that this assumption holds. There's a kind of a big, long, complicated name for when the standard deviation is not constant. It's called heteroscedasticity. And there are techniques to deal with that. But that's, well beyond this course. But this is something that we would want to at least take a glance at and see, do we see in that residual plot, does it seem like this assumption holds? Does it seem like our errors are reasonably independent? Does it seem like they reasonably have a similar standard deviation across the board? Okay. So I think that is all that I wanted to say before we jump over to Excel. Yeah. Right. Give me 1 second then to get my screens reset up here. And we'll start looking at, practically speaking, how do we get such models and evaluate whether they're any good. So I'm going to be pulling up number 3 regression demo here. Excel spreadsheet 3, if you want to get that put up on your end. Okay, so jumping over to this Excel spreadsheet, this is similar data or the same data that we saw last time. Remember last time we saw some things like, Google and gold that had a very low correlation, a correlation near 0. Well, a correlation near 0 suggests that there's really not a linear relationship between the two variables. It doesn't really make sense then to try to run a linear regression and describe the linear relationship when it seems like no such relationship really exists. So we're going to start by looking at Google and Yahoo that had a correlation of 0.8. Correlation of 0.8, that's getting up close to +1. It seems like there's a good bit of linear relationship that exists between these two variables. And it does make sense to try to extract some more information about that, try to describe that linear relationship with a regression line. And that's what we're going to do here. So we're going to have Excel crank out a sheet that looks like this. And before we have Excel crank out the sheet, I just want to take a glance at the sheet and see what are the things that we're going to be interested in. Let me blow it up a little bit here so you can see it a little better. We get a lot of information here. We get an ANOVA table, which analysis of variance. Again, we'll talk about that in a couple of classes here, but it's not super important for what we're talking about here. We get some other things up here, like just some other statistics. We get some other information down here. But there are a couple of things that I really want to highlight, the things in bold. Under regression statistics up here, we have the quote multiple R. For our purposes, this is just the same as the correlation coefficient. It can mean something slightly different in some other context. That's why it doesn't just say correlation coefficient, but multiple R is the correlation coefficient, and that's 0.79. We also see R square. What is that? Well, remember the goal of this linear model is to try to kind of describe the relationship between X and Y. In other words, my goal is to describe changes in Y using changes in X. So what is R squared? Literally the square of the correlation coefficient, just literally the correlation coefficient multiplied by itself. Well, this is what we call the coefficient of determination. Sounds very official and maybe a little ominous or something, but the coefficient of determination, and what it says, remember, r is between 0 and 1. So r is between -1 and 1. So r squared is between 0 and 1. This is the proportion of the variation in y explained by variation in x. So that's what the coefficient of determination is. That's what the square of the correlation coefficient tells us. I mean, it doesn't necessarily seem like just squaring the correlation coefficient should have this, this property, but it does. Why wouldn't taking the absolute value give us this property or whatever? But it turns out that squaring it is the right way to do this. And this is essentially a component of how good our linear model is. If we set up a model and we only explain 10% of the phenomenon we're trying to explain, that's, at least in most situations, not a very good model. Probably not very useful to just explain 10% of what's going on. If we explain 95% of what's going on, that's probably in most situations a great model. If I can explain 95% of the phenomenon that I'm trying to explain, I'm probably pretty happy with that. What do I get out of this model? Well, in this particular instance, I get 63%. I'm explaining about 2/3 of what's going on and leaving unexplained about 1/3. I'm probably pretty happy with that in most situations. So this r squared is kind of the explanatory power of the model between 0 and 1. And if I'm explaining 2/3 of what's going on, maybe I'm pretty happy with that. The other thing where I want to find out if this is a good model or not is, well, let me just rewrite that. In population terms, I have y equals alpha plus beta x. So if I had access to the whole population, I could run this this algorithm and I could figure out alpha and beta. I could figure out the slope in particular for the whole population, for all of the data. But usually I just have a sample. So I'm estimating beta by, say, b or beta hat, whatever you want to call it. And that's based on the sample. Well, if I get a slope coefficient that was 0, so what if beta is 0? Then that means actually I just have like y equals alpha or something. Well, but if beta is 0, there's no linear relationship. If beta is 0, I'm trying to describe a linear relationship that's not actually there. The coefficient of the linear term is 0. So that would be kind of a silly thing to do. So my question is, well, do I think that the actual population slope is 0? Well, I get b from my sample. I get an estimate for it from my sample, but I can't just say, well, since that estimate is non-zero, I'm very confident that the population parameter is also non-zero. I want to do something like either a hypothesis test or a confidence interval and see what happens. So I either want to look at a confidence interval, say, in this case, a 95% confidence interval for the slope for beta. Is what? 16.9 to 26.3. I note that 0 is not in that interval. And so I'm pretty sure that the slope is not actually 0, that there is actually some component of linear relationship between these two variables. And that using a linear model, at least isn't an outright silly thing to do. Or I could look at a hypothesis test. We kind of have seen in chapter 7 and 8 that hypothesis tests and confidence intervals operate in some sense very similarly. So I could ask, if I have two competing hypotheses, one is that beta is non-zero, that there is a linear relationship between the variables, that this coefficient of the linear term is not zero. That's my alternative hypothesis. That's what I'm trying to demonstrate with the data, that a linear relationship does exist, and therefore it's sensible to describe it. I test that against the null hypothesis that beta is zero, beta equals zero. A small p-value means I reject the null in favor of the alternative and conclude that there is likely a linear relationship. I should be very careful. I almost talked like a Bayesian. If p is very small, so p less than 5%, less than 1%, I would reject the null in favor of the alternative, and I would conclude that beta not equal to zero, that there is a linear relationship between the two variables. I don't want to say it's likely there's a linear relationship between the two variables, because that's a non-frequentive statement. But I note that the p-value is about 10 to the minus 12. That's what the e here means. It means e is exponent like times 10 to the power minus 12. This is certainly less than 1% or 5% or whatever reasonable alpha that we would put down there. 10 to the minus 12 is a tiny number. We can say this is very strong statistically significant evidence in favor of a linear relationship between the two variables. So these are the two things we want to check. We want to check that we have a reasonably high R squared, that our explanatory power is reasonably good, and also that we're reasonably certain that the slope variable is not zero. That we're not trying to do something like describe something that has no linear relationship with a linear model. That would be kind of a silly thing to do. Okay, so how do I generate this table? Well, I generate this table using the data analysis tool pack. So if I go to my data tab, I should see data analysis up here. Now, just because occasionally it's not up here, I think we've added it in the past, but you might be using a different computer or something like that, or your settings might have gotten reset. So let's just go through how to add that in. If I go to file over here on the left, to the left of home, I go all the way down to options. And I have this window Excel options. I go all the way down to add-ins. And I want to manage Excel add-ins here at the bottom. So I'll just click go. And here, if analysis toolpack is not checked, then I just check it, click OK, and I should have this data analysis bit pop up again under the data tab up here, data analysis. So that's what I'm going to use here. We used this previously for things like one variable stats or maybe drawing histograms, some of that. But I'm going to use data analysis, click that, and it comes up, and we've seen, again, like histogram, we've seen descriptive stats here, but I'm going to look for regression. So I'll click on regression, I'll go OK. And now it says input Y range. So what's my output? I'm going to use Google as the output here. I'm going to include labels so that I know what I'm talking about. It'll keep the labels straight that way. So I'm going to include labels, and my Y range is going to be from the Google label on C1. I'll click there, I'll hold Shift, and I'll click C54, and that just selects all of the cells that are between those two. My X range, similarly, input X range, I click in that text box. I'm including the label, so I'll include Yahoo, B1. Scroll all the way down, Shift and click at B54. Now Excel is going to assume that these two lists are the same length and that you have things paired up properly so that each, respective line goes with, the B and the C go together. I have my labels. Okay, good. I'm not going to check constant as 0. That would be if I knew that alpha was 0 for some reason, I might check that. Like if I had d-meaned the data already or something, but I'm not going to check that because I don't know that. I will check confidence level 95%. I think it's the standard anyway, but if we wanted to change it to 90 or 99, we could do that here. I'll have it output in a new worksheet play. That looks good. I do want it to list the residual plots or the errors because I would like to take a glance and see if I think that this assumption is satisfied. You could plot other stuff too. There's other things you can have it output here, but we'll just stick with this. I think that's probably pretty good. And here's what we get as output. Let me just select up here and double click to, if you double click the edge of one of these columns up on the top, it'll resize the columns all for you. So now we can see everything. And we do see this. We do see this R squared of 63%. So that's the coefficient of determination, the explanatory power of the model. Oops. We do see the p-value of 10 to the minus 12 and the confidence interval that does not include 0. So that tells us that we have statistical significance, that the slope coefficient is not 0. If I look at my residual plot, let me try to make this a little bigger. There we go. If I look at my residual plot, this might be a little concerning. It does seem like when we're further to the left, when Yahoo is lower in value, it does seem like the residuals are larger, that there's a larger variance there. And when Yahoo's higher, when that's a higher value, it seems like the residuals are a little smaller. Maybe we have a little bit of heteroscedasticity going on here. Maybe we would question whether we have a constant standard deviation or whether we have independence between these residuals. That might be a fair challenge to this model. Maybe we'd be a little bit worried about using this model because of that. But let's suppose that we're going to use this model. Then what does it tell us? It tells us that the intercept for our model is 304, and the slope coefficient of Yahoo is 21.6. Or in other words, it tells me my model is that my estimate for Google is 304 plus 21.6 times the Yahoo stock price. This model should explain about 63% of the variations in Google using variations in Yahoo, and will leave unexplained, something like a third of the variation in Google. Not a terrible result for as simple as this model is in a sense. I'm just using one stock and just the linear relationship. And what I've done here is I have my slope and my intercept. I've made another column for the estimate. It's going to be the slope times the Yahoo price plus my constant of 304 or so. So when Yahoo's 23.47, my estimate would be that Google is $811. When Yahoo's 20.5, my estimate will be that Google is $747. But we see that our estimates and the actual values for Google for these Yahoo inputs don't perfectly align. But if I graph this estimate line, this red line, I can see my regression line plotted on the same plot as my scatter plot data between Yahoo and Google. And I can just visually look at this and maybe I'm a little bit skeptical of what's happening on the left over here, because it seems like when we're on the left, more of that data is far away from the line. But I noticed that as soon as we go to the right even a little bit, the data really tightens up to that line nicely. So again, maybe I'd be a little skeptical of this model because of this seemingly larger variance here on the left and this kind of deviation from the model on the left side. But maybe I'd be happy using the model because of the pretty decent R squared, especially considering a simple model. The low p-value indicating that there's strong statistically significant evidence that that the slope of the that the slope coefficient or the coefficient of the linear bit is non-zero, and the simplicity of the model. Maybe I would be willing to use this model. So it's a little less clear cut than something like, when we ask, is this a good model? Is this one you'd be willing to use? It's, I think, a little less clear cut than something like a hypothesis test where you run through an algorithm, you get a yes or no. It's a little bit more of a judgment call. But this one, I think this would be kind of on the, probably good to use side of things. I'm going to skip over, I did some examples here with d-meaning and so on, but I'm going to skip over that for now. So let's take a look at the PIMCO versus Microsoft example. Remember, this had a correlation of about 0.7, so not quite as strong of a correlation as Google versus Yahoo. Not quite as strong of a linear relationship. I would expect my numbers that I get out of here for kind of how good the model is to maybe not be quite as nice as the Google Yahoo. But I think this, 0.7 is still a reasonably high correlation, kind of reasonably close to +1. So maybe I would think that I can get a decent model out of here. Again, let's go to our data analysis tool pack. We'll go into regression. We'll keep the settings the same. So we'll include labels, 95% confidence level. I'll put in a new worksheet apply, and I'll put residual plots. My Y range is going to be the same. These spreadsheets are set up the same. So same column, same data for the output. And same column for the input, B1 to B54. If I had spreadsheets that were set up differently than one another, I would have to adjust these X and Y ranges, but I set them all up the same so that it would be a little easier. Click OK. And here again, everything's kind of scrunched together. So I'll just click up here on this A up top. I'll double click and select all the way over to this last column. So I selected A through I up top just by clicking and dragging. And then I'll go to the right edge of this block up here with I, right between I and J, where my cursor turns into this little kind of double sideways arrows thing. And I'll just double click, and that'll automatically resize everything so it's easier for me to see. I see an R squared of about 50%. The explanatory power of the model, or how much of the variation in Microsoft is explained by variations in the PIMCO price, is about 50%. Not as good as the little bit above 60% as we saw before, but again, for a simple model, for a fairly complex phenomenon being explained by just one other security, maybe that's maybe I'm happy with that. 50% explanatory power for a simple, easy to understand model. Do I think that the slope coefficient is actually 0 if I had access to population data rather than sample data. Well, I look at my p-value, 10 to the minus 9. Well, that's certainly significant. It's less than, 1/20th or 0.05. It's less than 0.01 or 10 to the minus 2. 10 to the minus 9 is going to be a very significant p-value, highly significant. So I have strong statistically significant evidence in favor of the slope coefficient not being 0. I'll also look at my residuals. Again, I'll blow this up just a little bit. And I mean, I don't know, I could buy that that's maybe normally distributed. It's just kind of a big smattering of a bunch of points. I don't see any real patterns. It doesn't look like the standard deviation is different, say, going from the left to the right. Maybe a little bit in the middle here. We have a couple of outliers in the middle, but I don't think there's really enough evidence to say that the standard deviation is different at different places or that there's a lack of independence. So, I mean, this doesn't look terrible. And then I can do the same thing that I did for Yahoo and Google. I bring over my intercept and slope for each of my PIMCO Microsoft order pairs. I have a Microsoft estimate based on the slope and the intercept that I get out. Then I can plot these estimates as a red line here. And this red line is my regression model. The blue points on the scatter plot are my actual data points. And I always want to just take a look at my model and see if it looks reasonable. And in this case, it does seem like it looks reasonable. We do have a couple of stray points over here that we also kind of saw up here in the residual plot. But overall, I think this line does stay pretty close to most of the data points. This is probably a good regression result. Maybe doesn't have quite as high of an explanatory power as the previous one, but still probably a good result. Now let's look at an example of a bad result, and this would be like pretty much worst case scenario. Give me 1 second here. Okay, so let's look at this result between Google and Gold. Now remember, this was one that had a correlation about as close as you can get to 0, negative 0.01. So we think from the correlation coefficient that there's essentially no linear relationship between these two variables. Right, the correlation is quite close to 0, no linear relationship. It is kind of a silly thing then to try to describe the linear relationship with a regression line. But let's try to do it and see what happens. Like, is the computer just going to blow up? Is Excel going to tell me this is a horrible model, don't do this? Well, no. It just gives me output. It gives me the same screen that I got before. I have to know how to interpret the output. So my explanatory power is about 0. 0.0001. I'm explaining, what would that be? Like 1% of 1% of the variation in Google's stock price using what's essentially the price of gold, the price of a Spider Gold share. If I'm only explaining 1 part in 1,000 of the thing I'm interested in, that's really not a good model. So I wouldn't be happy with this model because this R squared is so low. 10 to the minus 4, I'm not really happy with that. What do I think in terms of this, in terms of the hypothesis test? Do I think that it's unlikely, or do I think that it's that the evidence is so inconsistent with a slope of 0 that I would reject the null in favor of the alternative and conclude that the slope is non-zero. Do I get a p-value like less than 5%, less than 0.05, or a p-value less than 0.01? My p-value is 0.92. My p-value is 92%. That's certainly not less than 5% or less than 1%. It's certainly not less than a number that I would establish as my significance level. And furthermore, if I look at my confidence interval, my 95% confidence interval for the actual slope variable, or sorry, the coefficient of the slope variable is -3 to +3. 0 is in that interval, right in the middle of that interval. I think it could certainly be true that beta is actually 0, that there's actually 0 linear relationship between these two. However, despite all of that, note that it still gives me output. It still gives me a slope for gold and an intercept that are the slope and intercept for the best linear model. It still gives me a best linear model. I can still come over here and bring my slope and intercept over, compute my estimates, same as I did before. Plot the line on the same scatter plot. I can do all the same stuff as before. It didn't blow up. It didn't refuse to give me an answer. It gave me a best linear model. This is the best linear relationship. This is the best we can do. But in this case, the best we can do is not good at all. It has essentially 0 explanatory power. We're trying to model a situation where it seems that there's no linear relationship between the variables. We're trying to model that with a linear model. That seems like a silly thing to do. And if we just look at the picture, it looks terrible. Right? This red line, I mean, how are we going to say that that is a reasonable model of the data set that we see here? I don't think that's a reasonable conclusion at all to make. This red line is not doing a good job at all of modeling this data. Or in other words, if I knew that like spider gold shares were 155, that I'm like in the middle here, would that give me a really good idea of where Google is versus if it was 170? Well, no, like it really doesn't give me any information at all about Google. So this would be quite a terrible result. It's still the best linear model we can do. It's still the choice of slope and intercept that gives us the best result as far as minimizing the sum of the squared errors up here. But the best that we can do for this particular data set is just not good at all. Okay, I think we will stop there today. When we come back, we'll talk about a little bit more in this Excel file. We'll finish up this Excel file. We might talk a little bit more about correlation and regression in the fourth Excel file, the second one that I put in the chat today. And I think that'll just about wrap us up as far as correlation and regression goes, at least as far as we're going to cover it in this course. And so next time we should probably spend about half of the class finishing up correlation and regression, about half of the class starting into chi-square tests, and then the following Monday, finishing up chi-square tests and discussing a bit of ANOVA. And again, I'll have the chi-squared and ANOVA supplements posted in the near future on the YouTube channel. So if you wanted to watch those ahead of time and take the exam, the final exam a little bit early before our Monday class meeting, you're free to do that. All right, so with that being said, unless there are any questions, we'll call it a day for today, a few minutes early, and I will see you Wednesday. All right, see ya.
Yeah, Professor Yost, I just got one quick question. In the final exam, will we be given like a tables like